Greetings to everyone. My name is Chinmay Vinay Dandavate. I am a student of MSc Semester 1 Statistics in the Institute of Science, Nagpur. And the topic which I have selected for the seminar is Fischer's information and information matrix. So, before we jump to the topic of Fischer's information and information matrix, we would like to start with a preface, and that preface is likelihood. So, in order to understand what is likelihood, I think it is essential to first know what is the difference between likelihood and probability. Now, in order to understand what is the difference between likelihood and probability, first we need to know that how they look very much similar to each other. Now, in order to realize the similarity between these two, let me put forth in front of you two statements. Let us suppose they are picked up from two different national dailies. Okay, the probability of increase in college fees next year is 70%. This is the statement with respect to a certain state. It is published in a certain national daily in on a certain day, and in some other national daily on the same day with reference to the same state, same news, there is another headline, and that headline is that the likelihood of increase in college fees next year is 70%. Now here the content of both the statements is same. It is with respect to the same situation, the same state, the same topic. So can I say that both of these statements are equal to each other? The answer is yes. But when we get the answer to this question whether they are same or not, immediately there arises another question, that if these two sentences are equal in meaning, so does it also mean that probability is also equal to likelihood? In our day-to-day usage and in our daily life, these two terms might be interchangeable or they might be having an equal meaning, but in the statistical terms, probability is not equals to likelihood. But if it indeed is not equal, then it is very much essential to know what is the difference between these two. And in order to know that difference, I would like to motivate that difference by the means of an example. Now, the example is that we consider the distribution of the mouse weights. Fine, we have a bunch of mice, and we plot the graph of their weights with the x-axis denoting the weight of the mice, the y-axis denoting the number of mice. Okay, so this is our distribution curve with the mean weight of the mice being 32 gram, the lowest observed weight being 24 gram, the highest observed weight being 40 gram, and the standard deviation being 2.5 gram. Now, let's say we are interested in finding that what is the probability. Note the term very much carefully. What is the probability of finding a mouse to have weight between 32 gram to 34 gram? So, the probability of the weight of any randomly selected mouse to be between 32 gram to 34 gram is, let's say, 0.29. Let's consider that this is a given fact, that the probability of the weight of any random mouse to be between 32 to 34 gram is 0.29. So mathematically, this fact can be represented by this equation: probability of weight lying between 32 gram to 34 gram provided the mean is 32 gram and the standard deviation is 2.5 gram is 0.29. So how can this fact, this probability, be represented on this graph? So this probability can be represented on this graph by denoting it by the area falling under this particular interval of 32 gram to 34 gram. This is probability. Now we move to likelihood. To talk about likelihood, let us assume that the mouse is already weighed. Okay, we are not interested in finding whether it is in between a certain interval or not. Already we know its accurate weight and say it's 34 gram. So now, if I pick a random mouse So what is the likelihood of weighing a 34-gram mouse? And that can be expressed on the graph as, we again take a graph with the x-axis denoting the weight of the mice. We plot 34 gram on the x-axis. We drop a perpendicular on the curve, distribution curve. Here we have a point, and from that point we again drop a perpendicular on the y-axis to know the likelihood, and that likelihood, let's say, is 0.12. Now we try to put forth this statement in the mathematical form as we did in the case of probability, and let's say that the statement is like this: likelihood given mean equals to 34 and standard deviation equals to 2.5, provided the weight of mouse is 34 gram, is 0.12. Now here we can see the shape and location of the distribution, the shape of this curve. It is completely decided or can be possibly altered by the value of these two constants, that is mean and standard deviation. Whereas the information which is given here, the in the case of likelihood, the measurements which are on the right side of this slash, they are fixed. So in order to summarize the difference between the mean and likelihood, we can say, in summary, probabilities are the areas under fixed distribution. You can see we have these areas. Here the distribution remains constant, but the area under the graph can change. In our example for finding the probability, we were trying to know what is the probability that a mice will have a weight between 32 gram to 34 gram. Now this range can change. It can be between 19 to 24. It might be between let's say 15 to 30. It might be anything. So here the area under the graph can change as per our requirements. Here we can see that there is data given distribution, that is the distribution is fixed, whereas in case of likelihoods the y-axis values or the ordinates, they are representing the likelihood, and here the data points are fixed but the distribution can change as per our requirements. That is, distribution is to be the concern provided the data is given, and that can be represented like this. Fine. So now that we have dealt with what is the difference between likelihood and probability, we move to our topic: what is log of likelihood and why do we need it? Fine. So as we have seen that in likelihood, now say in the prior example we were having only one factor, that is the weight of the mice. But in many real life situations there are many factors which contribute to what would be the likelihood of a certain factor or certain thing. Now this somehow is a joint likelihood. However, we assume that each point is independent of each other, and the existence of one point or existence of one factor doesn't determine the existence of the another factor or another point given in the given distribution or mathematical model. So after looking at this term of likelihood, we can say, since we know what is the independence theorem of probability or likelihood, we can say that likelihood of x given a, b and c can be equal to likelihood of x given a into likelihood of x given b into likelihood of x given c. Now what does the mathematical operation of log do? The function of the mathematical operation of log is that it aids the calculations further by giving two important aids or two important let's say helps or mathematical facilities. The first facility is that the exponentiation is turned into multiplication, that is log of a to the power b is nothing but b into log of a. And the second mathematical facility is that multiplication is turned to addition, that is log of a into b into c into d becomes log a plus log b plus log c plus log d. So this is the reason why we need to have this log of likelihood to aid the further mathematical calculations as well as to have help in the derivations of further theorems and proofs. Fine. So having dealt with what is log of likelihood and the reason why we need to have it, we move to the topic that we have this function of likelihood, we have these constants. After looking at these three constants, there immediately arises a bunch of questions into my mind, that what are these parameters? What are these parameters A, B and C? And how can they contribute to the likelihood of X? How can they ensure that the likelihood of X given these three parameters is maximum? Now this somehow pushes us to the concept of what is a maximum likelihood estimator. Fine. So maximum likelihood estimator is nothing but the statistical technique by which we choose these parameters in such a way that they match or fit to the observed set of values to the maximum possible extent, which can be further mathematically done by differentiating the likelihood function, that is d by dx of likelihood of x given a, b, c, and further equating it to 0, which is very famously known as the maxima principle. So this is what is the maximum likelihood estimator, that it chooses these parameters in such a way that the likelihood of our desired value becomes maximum. Fine. So now moving ahead, we finally come to our topic after having dealt with such a vast and thorough background. We finally come to our topic, what is Fischer's information. So Fischer's information, we have this probability of x given theta is same for all values of theta. We have two extreme cases. Okay, probability of x given theta where theta is constant is same for all values of theta. Okay, then x does not provide any information about theta. Since any parameter of theta can have that value x, we know that the value is same, so any value of theta can give this value x. Now we have second case. Probability of x given theta is non-zero only for a single value of theta. Then x provides complete information about theta. So these are two extreme cases, but these are exaggerations of possibilities as far as the real life scenario is concerned. Fine. So they being extreme cases, the Fischer's information can be generalized as I of theta. I of theta is the mathematical denotation for the Fischer's information, and it can be denoted as expectation of d by d theta log of p x given theta whole square. Now we know that we have to maximize the likelihood, so we have done this d by d theta, and we know that these are two extreme cases and we need to normalize it, or we need to make sure that the values are moderate. So what we do is we take the mean, and we know that mean is given by the expectation, so we here take the expectation. So thus it is the measure of the amount of information a random variable carries about the parameter. That is, now in terms of the example of that mice, so it denotes that what is the, now let's say we are having certain, now leave alone the example of mice, we have human beings. Let's say we calculate the hemoglobin of a certain human being. The value of the hemoglobin being the random variable, and the factors being the nutrition which he or she is getting, the exercise he or she is doing being another factor, A being the nutrition, B being the exercise, and C let's being the uh, sleep which he or she is getting. So here the X, that is the hemoglobin, it is the measure of the amount of information this random variable. Fischer's information is nothing but the amount of information the hemoglobin carries about these three parameters. That is, by looking at the hemoglobin itself, we can know, or we can get an idea of what is the nutritional content that person is getting, what is the amount of exercise he or she is doing, and what is the amount of sleep he or she is taking. This is what Fischer's information denotes in the practical terms. Fine. So now we come to our second topic, that is what is Fischer's matrices. So in case the parameter about which information is to be found is a vector. Now up till now we have been dealing with mice, their weights, we have been dealing about humans, hemoglobin, their sleep, their food intake, exercise, etc. But in many industrial and professional situations, there come certain cases where the parameter about which the information is to be found is a vector. That is, it is a physical quantity which is having many directions, many dimensions. In such a case, the information is not presentable in the form of a single line statement, but it needs to be presented in the form of matrices, where the columns and the rows, they denote the number of factors as well as the direction of each factor or the vector of each factor. Such matrices in which the Fischer's information about the parameters is expressed in form of matrices are termed as the Fischer's information matrices. Fine. So I am done with all which I had prepared for delivering in this seminar. It's the time for acknowledgements. So these are the resources which I used for designing this seminar. So I thank you for all your time and your attention. Thank you.